Hey everyone, welcome to another RISE webinar Journal Club. And today we have the pleasure of um, hosting Ricardo Gonzales. So I'll briefly introduce the speaker and then he will talk about his work. And then please feel free to ask questions in the Q&A box at any time. And uh, he will try to answer the questions. So Ricardo Gonzalez is a postdoctoral researcher at Harvard Medical School and Massachusetts General Hospital. He develops trustworthy medical imaging systems that translate complex biomedical data into reproducible biomarkers, analysis tools, and reusable scientific infrastructure. He earned his PhD in medical sciences from the University of Oxford and his degree in electrical engineering from University of Engineering and Technology in Peru. And today he's going to talk to us about making AI models and datasets more transparent. Ricardo, take it away.
All right, thank you so much, Pulkit, for the kind introduction and invitation to present here. I consider this is an excellent initiative to get to know more about the field and to learn from each other. So, yeah, today I will be talking about making AI models and datasets more transparent. So I want to tell you about the specific project that I have been part of. And this one has one specific goal to take the evidence about medical AI model, which today is scattered across different sources, and it can be placed into something more structured, searchable, and reusable. So throughout the presentation, you will see three moving parts, and they map onto the arrow that is at the bottom of this slide. So first, we have a shared vocabulary, an ontology called roadmap, so that everyone describes a model or a data set with the same terms. Then second, we have a public library, Atlas, the RSNA annotated library of AI systems, where that vocabulary becomes real cards that you can search. And third, we have the automation, because nobody's going to fill in 80 fields by hand from scratch. So we use LLMs to pre-fill the cards and humans to create them. So along the way, this work has produced 2 papers in Radiology AI this year and 2 conference abstracts over the last 2 years. So I will pull evidence from the 4 of them, and then we can discuss that. So let's start with the problem itself. So here's the problem in one slide. We try to answer a simple question as an example: which published MRI models for a given task were validated on an external test set, and what did they report? So if you want to find that answer, the information exists, but it is scattered. It lives in the paper, in supplements, code repo, on a challenge page, on a dataset page, even sometimes in a vendor model card, and even sometimes as well in regulatory summary. So each source uses its own terms and its own level of detail. So the evidence is information rich, but it's really tricky to aggregate. The roadmap paper makes this point directly. So despite model cards, data sheets for data sets, fact sheets, or even nutrition labels, no universally accepted standard harmonizes medical AI metadata. And importantly, none of the existing ones covers both models and data sets altogether. So the opportunity is on the right. Take the same details we already publish and make them standardized, searchable, interoperable, comparable, and reusable. So in one phrase, to move from distributed documentation to curable metadata. But there's also one honest caveat now, because it runs through the whole talk. Structuring evidence makes gaps visible. It does not by itself close them. So keep that in mind while we go through the presentation. So here's the whole project in one slide, and it is the map for the rest of the talk. So again, part 1 is the vocabulary. That is a roadmap, the radiology, ontology of AI datasets, models, and projects. It's a ontology, meaning a formal computer interoperable set of terms and relationships. It is what let us all describe a model or a data set the same way. The part two, we have the library, that is the Atlas RSNA annotated library of AI systems. This is where the vocabulary stops being an abstraction and becomes actually a JSON card that sits on a public website and can be searched, compared, and reviewed. On part three, and this is a part that decides whether any of it survives contact with reality, a way to fill the library. And again, nobody's gonna hand enter many structured fields per paper from scratch. So we use LLMs to pre-fill the cards from published manuscripts and humans to create what comes out. The evidence behind those three parts is that the band at the bottom. So again, 2 papers of Radiology AI this year and the conference over the last 2 years. And we will now start with the vocabulary. So let's be concrete of what an ontology actually is. So it is mainly 2 things: a set of formally defined terms and explicit relationships between them, written in a logic-based language. So here, the Web Ontology Language, OWL. So the contrast that matters is with free text. In a normal method section, external validation could mean whatever the authors decided it means that day. But in an ontology, each field has a definition, a pattern class, and a set of allowable values. What that buys you, and the paper is explicit about this, is 4 things. It reduces ambiguity in how things are described across institutions and studies. It enables semantic interoperability, so heterogeneous sources can be integrated. It supports computational reasoning, so a machine can infer, validate, and search. And because ontologies are extensible and versioned, they can grow with the science without breaking backward compatibility. So on the right, we have figure 2 from the roadmap paper. It shows some of the roadmaps, entities, and how they relate to each other. What I want you to take from here is the shape of the flow, entities connected by named director relationships. That is what computable metadata looks like. So having this in mind, we can extract the best of both worlds. LLMs can help with the scale, while ontologies can help with meaning. So you need both, and they do different jobs. So this is the architecture of the vocabulary. And on the left, we have figure 1 from the roadmap paper, the actual protege, a way to describe all these hierarchical relationship. And the top level class here is roadmap entity. It has 3 key subclasses: model, dataset, and project. That 3-way split is one of the genuinely distinctive moves here. So most prior schemes describe either model or they describe a dataset, model cards to models, data sheets to datasets, but roadmap does both, plus the project, which is where things like regulatory status and sustainability naturally live. So every entity carries descriptor items, and those are the chips on the right: intended use, out of scope use, intended user, input, output, data provenance, limitations, regulatory status, sustainability, and the social determinants of health. So I want to draw your attention on the last 3: regulatory status, sustainability, and SDOH. Most documentation standards stop at architecture or accuracy, asking about the regulatory pathway, the environmental cost, and the social determinants relevant to the population is ahead of where most of the field is. So whether people actually fill those fields is a different question, and a fair one to raise as well in discussion. And beneath the descriptors sit the specifics, so model properties like architecture and operating threshold, dataset properties like sampling, missingness, and subsets. So let's go through some numbers so you have a sense of the scale of this project. So as published, roadmap specifies 514 classes, of which 343 carry definitions. It has 20 object properties, which are the relationship types, plus 1 data property. It has 717 subclass relationships and 773 logical axioms, and all expressed in this standardized OWL. So I want to also be careful with the numbers. There was a lot of human creation that has been done in every single term, that it's already standardized and simplified so that it's ready to be used by the population. This ontology is already published on Bioportal, where you can browse it, download it, or hit it through an API. It is versioned, and it is still growing. So the counts in the paper are a snapshot rather than the ceiling. If you go and look at the live release today, most likely the numbers are already a bit larger. So that is actually a strength. It means that this project is maintained, but it also immediately raises the questions in the Navy box, which I think is the sharpest practical critique, at least as of now. So a standard that keeps moving needs maintenance and a version discipline. So who will be curating in the long term? And if the schema if the schema shift under you, what exactly does a card minted last year mean today? So we can hold the thought for the discussion as well. So a standard that invents its own private vocabulary just create more silo. Roadmap avoids that by reusing the terminologies that the field already uses. So on the left, we have RATLEX with more than 46,000 imaging concepts, the SNOMED-CT with more than 340,000 clinical terms, along with a lot of observation codes and the content codes from RSNA. But on the right is a work example straight from the paper. It is the RSNA abdominal traumatic injury CT dataset, RATIC in short. So look at how it is indexed. So there is a free text keyword, trauma. There's anatomy, liver, stored at RATLEX code RID56. And there's a condition, blunt injury of abdomen, stored as a long SNOMED code. And there are two contact codes for this, CT for computer tomography and ER for emergency radiology. In this particular case, each value is a specific code, not a word. That is what lets you ask, show me every emergency radiology CT resource involving the liver, and actually get an answer across institutions without anyone having agreed on phrasing in advance. So human knows hepatic and liver are the same, but a database doesn't necessarily know that unless you give it a code. The vocabulary would be half built if it just names models and data sets, but it stops at performance. So the second paper does for metrics what the first does for models and data sets. So 4 reasons that this matters. First, names collide. Sensitivity, recall, hit rate, and true positive rate are the same quantity with just 4 names, and different subfields default to different ones. If your card says recall and mine says sensitivity, a human sees the match, but a database doesn't. In the ontology, only one of them is the preferred label, and the rest are the alternate labels, which is exactly what resolves this. So second, metrics are heterogeneous. A curve, a matrix, and a single number are different kinds of objects. You cannot store an ROC curve the way that you store an accuracy value, and the taxonomy takes that seriously. Third, the choice drives the interpretation. So discrimination, calibration, fairness, and segmentation performance are different criteria, and they reward different models. Optimize one, and you can look excellent while failing another. Fourth, a metric is meaningless, stripped of context. It only means something alongside its formula, its bounds, and the criterion it is actually measuring. So which metric was used is not a footnote, it's part of the evidence, and it belongs in structured record. So here is what the taxonomy contains with the paper's own figure. We have 207 metrics, 8 15 performance criteria like classification, calibration, image segmentation, fairness, and text analysis, which specify what the metric actually measures, and 3 shapes, 11 graphical metrics, such as the ROC curve, the precision recall curve, the Kaplan-Meier estimator, 3 matrix matrices, and essentially the confusion matrix in its binary and multi-class forms, and 193 scalar metrics, the singular numbers like accuracy, AUROC, and dice. So figure 2 from the metrics papers on the bottom left, the thick arrows are relationships, subclass links. The dotted arrows are the interesting part. They connect a graphical or matrix metric to the scalar metrics derived from it. So the ontology knows that a confusion matrix is where true positive rate and F1 come from, and that AUROC come from the ROC curve. That means source data and summary statistic can be interpreted together instead of just floating free. On the right, it shows briefly how the list was built. We seeded with widely used metrics, search PubMed, Google Scholar, with a stated query, snowballed through citations in both iterations, and then deliberately extended into large language model metrics, fairness, reliability, and drift. That is reproducible, which is a real virtue, but also as a honest critic is a search plus snowball strategy that inherits the blind spots that the literature could sample. So comprehensive is a claim, not like a warranty. So now let me open one specific entry, because this is what separates a real control vocabulary from a list of names. So this is table 3, actually, from the paper of metrics, and the entry for true positive rate. So it has a stable identifier, roadmap with a number, and that in this case is 03339. Its preferred label is true positive rate, and sensitivity, recall, and TPR are recorded as alternate labels. That single decision is what solved the name collision problem I raised a few slides ago. It stores the formula, true positive over true positive plus false negatives. It records numerical bounds, lower 0 and upper 1. Its parent class is a scalar performance metric, and it is linked via the measures property to classification performance, the criterion it judges. It carries labels in English and Spanish, and I think Chinese is in the making, and definition cites authoritative reference sources, so you can just have more information from other published material. And on the right is why each of those earns its place. Alternate labels make my car and yours interoperable. The definition and formula make the meaning explicit rather than assumed. The bounds made automated sanity checking possible. So if you report a TPR of 1.4, it will get flagged by the machine. The measures links ties the number to what it actually judges, and the reference sources make every definition traceable rather than asserted. So as I said, there will be also a version in Chinese, which would be quite useful to make this resource internationalized. So far, we only have these 3 major languages, but it could be that in the future, we might release other languages as well. So now putting all these 2 halves together, we have a single card that carries 3 families of fields, mirroring the ontology branches. So under model, we have the intended use, and crucially, out of scope and excluded use, which almost nobody documents voluntarily, intended user, input and output, architecture, the operating threshold, what enormous amount of real-world performance quietly lives, limitation, regulatory status. Under datasets, we have the split role, whether this data was training, validation, or testing, internal versus external dataset, population and subset, sampling, missingness, the counts, such as the patients, exams, images, sites, imaging modality and procedure, image characteristics like resolution and pre-processing. Another evaluation, we have the metrics that work slotting in, the metric by its preferred label, its alternate labels, its formula and bounds, the performance criterion it addresses, what shape it is, what scalar metrics it links to, its reference sources, and its reported values. So here is the mental model that I want you to live with, and it's the line at the bottom. So the card is not a replacement for the paper, and it is not like a simplified summary. It is a structured companion, not less detailed than the paper, just more usable detail instead. Everything that was buried in prose now sits in a named field that can be queried, counted, and checked for completeness. So vocabulary is necessary, but it's not sufficient. Somebody has to actually use it. And that is exactly Atlas, RSNA annotated library of AI systems at atlas.rsna.org. An Atlas card is a JSON metadata document that conforms to a schema derived from roadmap. You don't need to handwrite JSON. The site has an interactive tools to create, edit, and validate cards against a schema. And there's a separate system that automatically generates preliminary cards by extracting information from the published documents, which is an automation strand that will come to next. The resources are indexed with RATLEX, SNOMED, and RSNA content codes, which is what makes them findable rather than just stored. On the numbers, but I want to be precise here because of the RISE. As of December 2025, Atlas included cards describing 70 models and 77 datasets, but it has kept growing since. And I would encourage you to just go and check in the website to see the updated numbers for this. And then the navy box is the part that I care about for our RISE audience specifically. So this is free, open, and API accessible, which lowers the barrier for groups in any setting to publish their work and be discovered. That is real. But submission is also voluntary. And voluntarily systems reflect whoever chooses to participate. So representative is something to watch, not just assume. So here is the objection that decides whether any of this survives. Documentation standards die because filing them is insidious. Nobody is going to hand enter dozens of structured fields for every paper they publish from scratch. So the answer is automation. And this is figure 1A from the abstract that we presented last year at RSNA, the actual pipeline. It's just 2 steps. First, an article goes into a summarizing GPT that has been given the roadmap field descriptions and example entries. Then that summary goes into a second, a structuring GPT that has the roadmap schema specified at its output format. And what comes out is a model card and a dataset card that are schema compliant by construction. For now, we have 2 steps because you're asking the model to do 2 different jobs, understand a scientific paper and then conform to a rigid schema. Splitting them is what makes it at least reliable for now. Ask one prompt to do both, and it may not do neither well, at least with the current version that we have. The cost line is also the one that surprises people, like using GPT-4o, extracting these fields. It took about a minute and 13 seconds per article, and it just costs about 5 cents. So the economics are not the barrier in this case, which means that the real question is not, can we afford it, but is it of any good? And that is exactly the next slide. So how good it is, at least from the little study that we did last year. We ran the pipeline on 54 articles from Radiology AI and had researchers rate every extracted subfield. Correct as is, worth 2 points, partially correct but incomplete, worth 1, and incorrect, worth 0. The result was that about 82% of extracted subfields were correct as is, 16% were correct but incomplete, and 3% were fully incorrect. Figure 1b on the left breaks that down by individual field, and it's worth looking at because the performance is not uniform. Some field the model nails, but others it routinely lifting. 2 nice robustness details is that model fields and datasets fields scored about the same. So 1.76 versus 1.78 out of 2, not significantly different. And there was no correlation between a score and paper length. So it does not degrade on long papers. But now if we take a look at it, honestly, in the navy box, we only have 3% that are outright wrong. That is genuinely good, but roughly 1 field in 5 is incomplete. And that means that about a fifth of the output still needs a human to finish it. That's like a strong assistant, but not an autonomous curator for now. And that's exactly what Atlas is intended to do from the beginning, that LLM could pre-fill, but then it comes human curation. The work that we presented this year with some updated models. We also did a model comparison between these frontier models. So we benchmark 3 frontier models on 10 papers. First, GPT-5, Claude, and Gemini 2.5. Each paper yields 76 model properties and 78 dataset properties. They're scored by experts on a 3-point rubric. And the leading model was GPT-5, but only for marginal difference with Claude and Gemini. So I also here want to be careful on how this gets reported, because the honest read is on the bottom right. Like the spread across 3 frontier models is about just 2%. So there's not a decisive win for anyone. If you told me that the ranking would flip with a different prom or a different 10 papers, I would also believe you. The engineering of the pipeline, the 2-step decomposition, the schema constraint matters more than which frontier model you plug into it. We then took the best model and ran it over the full corpus of 311 papers from Radiology AI and several public challenges, producing 283 models cards and 282 dataset cards at about 21 cents per paper. Those structure outputs are publicly accessible now through Atlas. So here's the capability that didn't exist before, and for me, it's one of the most exciting parts of the project. So once a few hundred papers are structured cards, you can interrogate the literature itself. Which metrics does a field actually report, as opposed to which ones we assume it reports? Which modalities and tasks dominate? How often is there genuine external validation? And who are these models actually built for? And most usefully, what is the demographic or labeling detail that is systematically missing? The last one turns equity from an anecdote into a measurement. So this is meta research enabled by structured. No new experiments, just the same literature made computable. The right side shows what the 311 paper corpus found. The most commonly reported metric was AUC. The most prevalent imaging modality was MRI. The most frequent use case was detection and diagnosis, and the most frequent intended user was radiologists. Now, if you read that carefully, this corpus is paper from Radiology AI plus some public challenges. So it's a mirror of the sample literature, not a census of all medical AI. If you sample a radiology journal, you will find radiologists. The finding is real, but it describes what this corpus reports, and I would not stretch it further than that. What is also interesting here is that AUC dominates, given everything we know about how badly AUC alone could characterize clinical usefulness. So what does the whole system let you do that you cannot do before? Mainly 3 verbs. You can do find which MRI models address detection or diagnosis and were validated on external test sets. Today, that would take some days of manual reading, and you could still miss things. With the structured cards, it is a query over just 4 fields. You can also compare which models report AUC, calibration, and subgroup performance on comparable data. Comparison is only fair when the fields line up, and the structure is the thing that makes them line up. This is where the metrics work pays off directly, because the ontology knows that your recall and my sensitivity are the same number. You can also review. This is one of that the editors and regulators could care about. And it could also drive adoption, like which required fields are missing before we sign off on this paper, this product, or this deployment. Because completeness is now machine checkable, and a missing operating threshold or an empty limitation field can be flagged automatically rather than slipping through peer review. And the bar at the bottom is the initiative on framing. Discovery, matching models to appropriate data sets, completeness checking, and detecting potential sources of bias. And I would flag the last one as is the most ambitious claim in the whole project, and we should also probably argue about it. So to place this fairly, here is a neighborhood, because none of this happens, it's just a vacuum. Documentation, model cards, data sheets for data sets, fact sheets, the model fact labels. This established that a card should exist and roughly what goes into it. The reporting guidelines, these tell you what to report and how to appraise quality. Metric selection, these tell you which metric to choose for a task. Notice that this is a job. Our metrics taxonomy deliberately does not do. It tells you what existing and what it means. It does not tell you what to use. Those are complementary. And adjacent ontologies like ITO, MCRO, these overlap and they raise a genuine consolidation question. So what is the actual claim here? Guidelines say what to report. Metrics tools say which metric to pick. Roadmap supplies the machine-readable substrate to store all of it. Atlas makes that public, and LLM extraction is the on-ramp for the decades of literature that already exist and are never going to be redocumented by hand. The specific gap it targets is that none of the prior work covers models and datasets together in one machine-readable schema. So let me put my own also appraisal on the table explicitly as one's reader's view. So you have also something concrete to disagree with. So what holds up? The gap it identifies is real. Model cards do models, data sheets do data sets, and nothing cover both in one machine-readable schema. It reuses the field's own terminologies instead of building another island, which is the difference between interoperability and a silo. It is not just a proposal on paper. It is deployed in Atlas, published in Bioportal with actual tooling for creating and validating cards under the institutional support of RSNA. And the regulatory, sustainability, and HDOH fields generally reach farther than most reporting guidelines do. But what I would push on, first and more important, reporting is not mitigation. This schema makes gaps visible. It enforces nothing. A perfectly documented card can describe a thoroughly biased model, and we should be careful not to let transparency infrastructure feel like a safety warranty. Second, adoption is voluntary, and that means uptake, not design quality, will decide whether this works. A beautiful standard nobody fills in is just a dead standard. Third, on the automation, roughly 1 field in 5 still needs human completion, so there is still some semi-automated process to be done. And fourth, the schema is built around fixed fields at a moment where the field is moving towards foundation models and agents, pre-training corpora, word race, agentic behavior. These do not slot neatly, at least yet, into the current structure. So to recap, the whole thing is in 3 sentences, is that roadmap gives you medical AI assured, machine-readable, vocabulary covering models, datasets, and projects with a rigorous matrix layer inside it. Atlas is where that vocabulary becomes public, searchable cards, and LLM extraction with human creation is what makes filling it intractable at the scale of the literature. The 2 papers are in Radiology AI, the Ontology is on Bioportal, and the cards are live at atlas.rsna.org, so all of it is inspectable, which is actually the point. Thank you so much for listening. I'm very happy to have contributed with an excellent tip at RSNA. I'm happy to also answer any questions you may have.
Yeah. Thanks, Ricardo. That was very insightful. Uh, I don't see any questions right now in the chat or in the Q&A. If folks have any questions, now is a good time. Uh, yeah, very interesting talk. I was wondering, I had a couple of questions. One, how, how would you implement this, let's say, when we submit a paper to MICCAI or any journal, how would people or authors would be encouraged to use this tool so that they can standardize their data sets?
Yeah, it's an excellent question. The uptake work is still in the making. There is the idea that now at least all paper from radiology journals, starting from RSNA, could already implement or adopt this type of data sheets of these structured metadata so that all papers that have been published there already have that set of information. And then the next step would be to just have meetings, talks with the other organizations like MICCAI or other journals that could also adopt this so that they can or they could invite the authors that have their papers accepted or already published to store these cards online. And another avenue of having this adopted is just by having the same website live, which already is, and invite the authors to just upload the papers, pass it through this LLM, have the pre-filled set of metadata, ask them to manually review it, and then have it published. So that could be as well another approach to solve this. And if not, another one would be just to do it a little bit more on the side. Has been a very interesting project that has been published recently where authors use this schema to go through a huge corpora of published literature and to check which models that are open access work on that have been implemented in a radiology AI topic. So they use this schema to go through this to all of these papers and then publish a comprehensive list having all these metadata included there. So that could also be another avenue in which the community can be benefit from.
Hmm, thanks. And I was also wondering, like, in your roadmap data, sorry, the roadmap paper. Um, so it's an ontology of medical AI models and data sets. So would you expect every paper that use this tool to advertise their paper? Do you also expect them to have their models and data sets open source, even if they have some restrictions on the data set? Or
Yeah, good question. I mean, from one side, it will tell you in which link the model is safe if it is either open source or not. At least you will have a link to like find more information about it that is present in the published paper. Um, and then when it comes to have it more searchable, that's also a huge benefit for the authors because if you want to find a specific model trained on this specific modality with this specific metrics, then it is easier to find that paper rather than just going through a huge list of papers in Google Scholar or another database. So the authors could also be benefit from having their paper more exposed to the community.
Hmm, I see. I think there's a question in the Q&A if you want to take a look. Just read
Yeah,
it out loud. And
sure. We have a question from Wayne Jean. So thank you, Ricardo, for your wonderful work. Thank you so much. I'm wondering if this framework can encourage more scientific rigor and ethical research in addition to the current contribution. I would love to contribute to this if you're interested. It's an excellent question. And it would definitely encourage more scientific rigor. There are already many guidelines like claim tripod AI that already guides the authors on how to be more rigorous when you are reporting your scientific findings and model developments, etc. And having ontology like this can help you For example, if you have a draft of your paper, you can pass it through this schema and then see what else is missing that you haven't thought about. Um, and that would quickly help you to know what you can cover so that the paper on its own can be more, reproducible, transparent, that you can describe all possible details you can think of. And also when it comes to the ethical research part, there is a development going on where this schema can also include these specific, let's say, criteria for some ethical guidelines or some um, reporting guidelines that once it is safe within the metadata, everything can be computed to see how fair it is, how compliant with ethical guidelines are. That is still work in the making, and absolutely we will welcome people that would like to participate. And if there is a strong match, we can definitely move forward, and I'm happy to be contacted later on if you would like to pursue that path as well.
I think, yeah, thanks for answering all the questions, Ricardo. I think those were excellent questions. I think if there are no other questions, then we can thank the speaker. Thanks a lot for presenting this wonderful work. Oh, yeah.
Thank you, Tara.
And, and if you have more questions, you can reach Ricardo directly at his email. Oh, I think there is one more question. Or
Oh, yes. I
yeah,
did some research on lower back pain, and this tool is interesting. I noticed that knowledge graph and meta models are also present, which are useful for ontological review. It would be interesting to integrate this. Yeah, for sure. It's a suitable work in progress that can also be benefit by overlapping fields. Thank you for the comment, Juan.
yeah, that's cool. Um, okay. I think we should end the session now. Thanks again, Ricardo, and thanks everyone for attending on this Saturday. And we will have this recording on YouTube shortly. And if anyone wants to recap what Ricardo said. So, yeah, thank you.
Absolutely. Thank you so much, Volker, and to all the audience. It's been a pleasure to present this.
Yeah,
Have a
thanks.
good week.
Bye. Have a good weekend. Bye.